Hello again. We were talking about the response of response analysis of multi-degree of freedom systems to dynamic loading. Okay, so we're looking at dynamic response of and here I have been talking about the fact that the kind of structures that we are referring to in this particular course is essentially that of your buildings, building frames, buildings, that kind of a thing. Okay. So, just to review the mode superposition method. Okay. The mode superposition method is based on the fact that where these are displacements corresponding to degrees of freedom. Okay. These are modal amplitudes, and this is the mode shape matrix. This is n by 1 because there are n degrees of freedom. This is n by 1 and this is n by n. Okay. Now, we can also say, remember last time we said that essentially the fact becomes, the problem becomes that in reality, you do not require all the modes to be considered, and therefore, if you were to look at it, we are saying that look, V is equal to phi into y, okay, where this is n into 1. This remains n into 1 purely because it is an n degree of freedom structure. So, these are displacements corresponding to each degree of freedom. This is no longer n by n, it is m by n by m. So, what happens is only considering m modes. Okay. So, where m is significantly less than n. So, that is the problem that happens, and note that you only have n is, this is a mode shape and there are only m mode shapes, and therefore, there are only m modal amplitudes. Okay. So, this is the beauty that we have taken this problem, we made it into a smaller problem, and furthermore, because of the orthogonality that you have of mode shapes, essentially what you come down to is the following problem. And then we talked about the fact that we could that is how we include damping, and we also saw where m n is equal to phi n transpose m phi n and p n is equal to phi n transpose p. Okay. So, this we have m such equations, okay, and you need to solve m such single degree of freedom problems, and you've solved the equation. Okay. So, this in essence, and then once you've got y n, okay, you've got different y n going from 1 to m, okay, then that becomes the phi, and then v you get by phi transpose y n, sorry, y, okay, and of course, this is subjected to y n 0 and y n dot 0, where y n 0 and y n dot 0 are given by phi n transpose m v 0 or v dot 0, both are given exactly the same way. The only thing is, if this is not dot, then this is not dot, if this is dot, then this is dot, okay, into phi n transpose. So, this in a sense is how you compute, how you go from, this is how you go from the original space to the modal space, and this is how you go from the modal space to the original space. So, these are the two opposite kind of relationships, and all of these are based on nothing but the fundamental fact that all modes are orthogonal with respect to each other. Okay. So, let me do one thing. Let us now look at a specific problem, and this is a problem that is a fairly well known problem, and I am going to list it out to you. Okay. This is, it's a 3-storied building with rigid beams, okay. So, what we have here is, this is V 1, this is V 2, and this is V 3, and the loads are given in this form: P, 2P, 3P, okay, where P of t is equal to P 0 sin omega bar t, where P 0 is 10 kilonewtons and omega bar is equal to 1.5 times the fundamental frequency. So, this is the loading, and if P, this is P, so this is 2P, this is P of t, 2P of t, 3P of t. Okay. So, this in a sense is the problem. Of course, we have to give the the way the masses in this thing, and we will say that this is weight W, okay, and so we will call it, sorry, mass M, and mass m by 2, and the lateral stiffness of this is given by 3K by 9, okay, and this is 7K by 9, and this is K, where M is equal to 10 tons or 10,000 kgs, and K is equal to 10 meganewton per meter. Okay. So, that these are all the parameters that are given to you. Okay. So, if we look at it, the mass matrix, what does the mass matrix look like? The mass matrix, you go through the procedure. I will not I'll give you what the mass matrix looks like. M 0 0. These are all massless. all of these columns are massless. So, all the mass is at this point. This is the mass matrix, and the stiffness matrix is the following: 16 K by 9 minus 7 K by 9, 0 minus 7 K by 9, 0, 10 K over 9. This is minus 3 K over 9, 0 minus 3 K over 9, and this is 3 K over 9, where K is given by this, M is given by this. Okay. So, and your displacement vector is V1, V2, V3, the lateral displacements at each story of the frame. Okay. So, this in a sense is the thing, and what we say is that, look, we are going to now remember that we never find out C over here, right. We found out M, K and the P vector. The P vector is the following: P, 2P, 3P. Okay, where P is given with 10 kilonewtons. Okay. So, what now? Now, the thing is, of course, to do K minus omega squared M into phi is equal to 0 and solve the eigenvalue problem. Here, I am giving you the solution to the eigenvalue problem, because we have already done that, and this focus is more on dynamic response than on free vibration response. Okay. So, I will give you the phi vectors. This is the first vector. The second vector .9827, .9829 and minus 1.9642, and finally, the third vector. There are 3 degrees of freedom. So, there are 3 vectors. The third vector is 1.5778 minus 1.1270, 0.4508. Okay. So, these are the 3 mode shapes. I am not going to give the frequencies right now, because we will see that we can actually derive the frequencies. Okay. So, if I rewrite this in the format of phi, so phi then becomes equal to 0.6375, 12750, 1.921, 0.9827, 0.9829 minus 1.9642, 1.578 minus 1.12, 0.4508, and phi transpose is equal to 0.6375, 1.270, 1.925, okay. Then 0.9827, 0.9829 minus 1.9642, and then finally 1.5778 minus 1.270 0.4508. So, once I have done, so this is nothing but look that this becomes phi 1 transpose, phi 2 transpose, phi 3 transpose, phi 1, phi 2, phi 3, and this is phi 1 transpose, phi 2 transpose, phi 3 transpose. Now, if I do now mass matrix, I have got the stiffness matrix. So, if I put phi transpose m phi and go through each of the multiplications, you will get the following. Okay. That is phi transpose m and phi transpose k phi is equal to 8.5. This is of course all kgs. This is going to be 8.5800 38.6 90 into 10 to the power of 6, because meganewtons, right. So, 10 to the power of 6 Newton per meter. So, now if I look at it, this upon this is, note two things. Diagonal means orthogonal property of both of these is satisfied. Well, that means that the phi values that we have given, which is these are indeed orthogonal mode shapes. Well, mode shapes are orthogonal, we have already found that out. Okay. So, here, so obviously this becomes what? So, your M1 becomes, what is K1? 8.58 into 10 to the power of 6 Newton per meter. M2 K2 M3 K3 Okay. So, having done that, I know that K1 upon M1 square root is equal to omega 1, because omega 1 squared is K1 upon M1, because we have already seen that K1 is equal to omega 1 squared M1. So, therefore, omega 1 is equal to K1, K1 is 8.58 into 10 to the power of 6 divided by 38,600. This is 14.909 radians per second. Omega 2 is equal to 38.6 into 10 to the power of 6 divided by 38,600. This one turns out to be 31.623 radians, and omega 3 is equal to 90 into 10 to the power of 6 upon 38,600, which is equal to 48.287 radians per second. Okay. So, essentially what we have here is that we have a situation where these are the frequencies, we've already got the m, all the m's, mn is equal to 38,600 kgs for n equal to 1, 2 and 3. And the only thing that we have left is what? Only thing that we have left is actually computation of the loads. So, P 1, P 2, P 3. So, let us look at P 1 of t, which is equal to phi 1 transpose into m into p. Okay. So, if you do that and substitute the fact that they are this thing, this one turns out to be equal to 89.250 kilonewton sine. Now, since we know 1.5, we know it has to be 14.909 into 1.5. So, that is equal to 22.3635 T. Okay, that is omega bar. Okay, that is P 1. P 2 is equal to phi 2 transpose m p, and that is equal to minus 2.441 kilonewton sine 0.365 T, and P 3 is phi 3 transpose m p, which is equal to 6.762 kilonewtons sine 22.3635. Okay. So, these are our P 1, P 2 and P 3. So, let us go to the next step. The next step is what? Is the fact that, let us write down the equation. We get the following equation: y 1 double dot plus omega 1 squared y 1 is equal to P 1 upon m 1. Okay. So, that's what we have, right. And so, if we go about it, I am sorry, omega 1 squared, and if we look at this, this is the single degree of freedom, okay, where P 1 t is of the form, let us say P 1 0 sine omega bar t, right. If this is the format, then what is the solution? This P 1 0, okay, is of this format. So, then what is the solution? The solution then becomes the following. It will be equal to, so y 1 of t, and this is the steady state solution. By the way, steady state solution, only the steady state solution. The steady state solution becomes the following: P 1 0 upon omega 1 squared m 1, okay, that is P 1 upon k 1 into 1 upon 1 minus omega bar upon omega 1 the whole squared into sine omega bar t. Okay. So, if you were to look at it, y 2 of t, I mean, let me put it this way, it will be y n p n m n into this sine omega bar t. That is the solution. Okay. So, if that is the solution, then y 1 is equal to P 1 is 8. I am now going to put it in newtons, because newtons and kgs go together. So, you have into omega n squared. So, that is 14.90 into 38.60 all upon 1 plus 1 minus. Now, if you look at it, omega bar upon omega 1 is 1.5, obviously that is how we have done it. Okay. into sine omega bar t. So, if you look at, so this is how it is, right, okay, because this is undamped system. So, therefore, it will directly have this. Okay. Now, y 2 of t is equal to minus 29441 upon, it is equal to, let me just have a quick look at it, 31.623. So, that is 31.623 squared into 38.00. 1 minus, now the thing is that omega bar is 22 and omega 2 is 31.623. If you do that, that turns out to be 0.7071 squared sine omega bar t. And finally, let me do y 3 on a separate sheet of paper. Y 3 max is y 3 t is equal to 6762 upon we had 48.287 squared into multiplied by 38.600, 1 upon 1 minus omega bar upon omega 3, 22.3635 upon 48.27, that turns out to be 0.4631 squared sine omega bar t. So, if we evaluate these, then we get that y 1 of t is equal to 8.3217 into 10 to the power of minus 3 meters sine omega bar t. Y 2 of t is equal to minus 1.5258 into 10 to the power of minus 3 sine omega bar t, and y 3 of t is equal to 0.0950 into 10 to the power of minus 3 meters per second. Now, these are all 10 to the power of minus millimeters actually. Okay. So, now if you look at it, if I were to put it together, now this is y 1, y 2, y 3. Do you notice something very interesting, that y 1 is large, y 2 is less, y 3 is even smaller. Okay. So, remember I said that the first mode is sometimes good enough. Okay. Let us see what we get. Okay. If you were to look at it, this would become the following. It would become that. So, let us now, so once I have got y 1 of t, y n of t, I can find out v by doing phi transpose y. Okay. So, now I can also say that look, v 1 of t is equal to phi. Now, here if you look at it, it is equal to the 1 n y n summation. Okay. So, now if I look at it, you will have the situation where that, okay, I will say, let me look at the first displacement in the first mode. That will only be what? It will be phi 1 1 into y 1. So, if I do phi 1 1 into y 1, I get 5.035 millimeters. If I were to look at the second displacement in the first mode, that is essentially equal to phi 2 1 into. So, the second displacement quantity in the first mode into y 1 will give me this. So, this is equal to 10.61 millimeter, and the displacement at the top is going to be 15.95 millimeter. So, in other words, V2 is going to be, so if you are looking at V1n, it is nothing but phi 1n, V2n is equal to phi 2n into yn, and similarly V3n is equal to phi 3n into yn. So, therefore, if it is phi 3 1, all of this is the first mode, the top, second and third corresponding. So, if you look at it, if I were to look back at this, this is what you multiply with y1, this is what you multiply with y1, this is what you multiply with y3 to get your V1, V2. Okay? So, similarly, we will get, these are the maximum values, amplitudes. Okay? These are the peak values. Okay? So, P21 is equal to 1.499 millimeter, phi 22, sorry, this is phi 12. In the second mode, first displacement 1.499, the second 1.5 V32 is equal to 2.997. By the way, this one is, please note that since this is plus, this is minus. So, when you are doing it with minus, what you get is that all of these are minus. Okay? And phi 1,3 is equal to 0.0931 millimeter, V23 is equal to 0.0665 millimeter, and V33 is equal to, please note that it is 1.5778 into Y3, okay, and all of those. So, you get V33 is equal to what? It is going to be smaller, and that is 0.0266 millimeter. Okay. So, this in a sense is your, these are your displacements. Okay. Now, all of them are with sin omega bar t. So, if I look at V 1 of t, it is going to be equal to this minus this plus this. Okay. So, that is V1. It is summation of all three of them. So, V11, V12, and all of them have sin omega bar t with them. Okay. So, you have a situation where you just add the 2, add the 3 and you get it. V2 is going to be this plus this plus this. So, this is minus. So, this will be 10.61 minus 1 point plus. Okay. So, you have a situation where if you look at it, we may as well neglect the third mode. Okay. Now, in this particular case, please note, and similarly we can find out V3 of t, which is this plus this sin omega bar t. Now, the question here becomes is that, look, since I have only 3 degrees of freedom, okay, I can neglect, I do not need to consider the third degree of freedom. So, actually I can make it into just solve the 2 degrees of freedom and be done with it. Okay. Now, this is a very peculiar situation where it is a harmonic load, and where the harmonic load actually the largest displacement is really in the second mode. Okay. That is a very interesting point to note, because the largest dynamic amplification that you have in this particular case is actually in the second mode. Okay. So, despite the second mode being actually dynamically more excited, because 1.5 omega 1 and omega 2 upon omega 1 is about 2, right. So, it actually comes very close to the second mode. So, even though I have taken a harmonic which is not tuned to the first mode, note that the first mode response is largest. Of course, the second mode response is not non-negligible, because actually since it is a harmonic load, this is excited. If you look at any arbitrary kind of load, you will always see that this is the extreme situation in which this contributed significantly purely because it is dynamically more excited. Okay. If you do not have that situation, you will have a situation where the total will almost be given by the first mode. Okay. Here I actually caused a situation where the second mode contributes more, I made it. However, you still see that the third mode is to be neglected. Okay. So, in actual fact, in reality, if we just deal with a 1 degree of freedom system in this particular case, you will have solved the problem. Okay. So, what is the takeaway from this particular problem that I solved? The problem that I solved are the following. One, I showed you how to use mode superposition to find out the response of a multi-degree of freedom system. Of course, in the multi-degree of freedom system, the first thing that you need to do is the free vibration analysis. Okay. Now, here I gave it to you because I have done it already. Okay. And then we went through the steps of the mode superposition analysis of how to go about it. Okay. And of course, here I just considered a harmonic load as a specific case of the form. Okay. So, now one, the procedure, we illustrated the procedure. Two, we saw that actually in a 3 degree of freedom structure, okay, the displacement quantity can pretty much be given by the first mode. In this particular case, because I gave the harmonic load, if I put omega bar very close to omega 1, you will see that omega, the second mode almost does not contribute. Okay. So, these are the points that you can actually reduce the number of degrees of freedom to illustrate the issue. Okay. Now, this is so much as this. Now, for displacements, this is the final point that I want to make in this particular lecture, and that is that in these kind of displacements, what happens here is the following, that for is typically sufficient, okay, or at the most 2 to 3 modes, even when you have, let us say, 1000 degrees of freedom. But if you are looking at force responses, for example, force responses, what kind of force responses are there? For example, the base shear, okay, or bending moment at a particular time, or story shear. Okay. If these are the things that you want to find out, then what happens is that you can go ahead and do this. Force responses, you require more modes. Now, why is that? Let us look at it. Let us look at what happens. If I were to look at this particular problem, okay. Now, typically, how would I find out the force response? Well, let us see. Let us take this particular problem, the specific example problem, but this is true of any kind of a problem that you have. V1, V2, V3. Okay. Now, I have found out V from phi y, right. I have found out my V. So, my V of t I have found out by doing phi transpose y, and this is typically m modes, and this is n by 1, and note m is less than or equal to n. Okay. Typically, we know that m is significantly less than n, but let us say that. Okay. So, that is my V of t. Now, how do I, for example, suppose I want to find out the base shear due to right. Now, note that these are, if there was no time dependence, if there was no inertia, what would V b be equal to? If it was static, what would V b be equal to? V b be equal to 6 p, right, and see p is equal to 10 kilonewtons. So, V b would equal to 60 kilonewtons. I would not need to have solved all of these, but note that these are time dependent loads, and so therefore, how do I find out my static? So, what I need to do is I have got my V. Okay. So, what I say is that look, under this load I have my V of t. So, I have V 1 of t, V 2 of t, V 3 of t. So, based on that, what do I get? I say that look, it was like this. I am just drawing line, okay, and these were. So, now what has happened is at any instant of time, this is V 3 of t at an instant of time. This is an instant at an instant of time t. This is V 1 and V 2 and V 3. Now, we say that look, how do I find my base shear? I say that look, let us take the situation. Suppose it was a static load. So, this is pseudostatic at time t. It becomes a pseudostatic problem. To get this displacement, what are the forces that I have to apply? Static forces, pseudostatic obviously, okay, which are going to give me these displacements? Well, we know that. What would be those forces? Those would be k into p, isn't it? See, in other words, at any instant of time t, to get a displacement given by this displacement quantity, okay, what would be the loads that I would have to apply? Okay, that is nothing but k into v. That is a known. I mean, that is something in a static sense, that is what it is, right. Okay. So, what we have is, and now look at it. How do I find out V b of t? It is this plus this plus this. But in other words, I can write V b of t as, note, see this. If I write this, 1 transpose, this is a vector of 1s, okay? Vector of 1, 1 1 1, okay? So, it is a 3 degree of freedom, 1 1 1. 1 1 1 into Fs. So, look at this, 1 into Fs1 plus 1 into Fs2 plus 1 into Fs3, which is nothing but a summation of this. This is equal to summation of Fsn. Okay. So, see, understand. So, Vb of t, once I get Fs of t, I can actually, for that load, I can find out all the force responses that I need to find out. Okay. So, Fs is equal to k into V. Okay. So, let us see what happens then when I have Fs equal to k into V. Fs of t is equal to k into, if you look at it, phi into y. Okay. So, if you look at this, okay, let us see what k phi is equal to. If you look at it, k into phi n is equal to omega n squared m phi n. Okay. So, if I were to look at it, then that I look at f s n of t. F s n of t would then become what? It would become equal to, let us see, what would f s n of t? It would be equal to k into phi n into y n of t. This would be this is the, if you look at it, well anyway, let me just put this down. Okay. So, if I were to draw this, okay, I can say that K phi is equal to omega squared into m into phi, where this is nothing but, look at this, this is n by n, this is n by n. Note that this is n by n, this is n by n, and this is n by n, where this is nothing but, if you look at it, it is a diagonal matrix where the first omega 1, omega 2, omega 1 squared, omega 2 squared, omega 3 squared. Okay. So, if I were to rewrite in this fashion, that I will say that, look, f s of t is nothing but summation of all modes going from 1 to n, okay, then f s n of t becomes this. And if you look at this, k phi n of t is omega n squared. So, I can write it in this form, that f s n of t is equal to omega squared m phi n into y n of t. Now, if I were to look at the base shear, what is base shear? 1 transpose. Okay. So, this is equal to, then V b of t is equal to omega n squared 1 transpose m phi n y n of t. This is 1 by n, this is n by 1, this is n by 1, okay, and this quantity, okay, is, now I will define a quantity L n. L n is nothing but phi n transpose m phi 1. Now, let us look at this. What is this? This is nothing but this phi n transpose m 1 transpose is equal to, look at it, 1 transpose m transpose phi n transpose, which is nothing but itself, and m transpose is 1. So, this becomes 1 transpose m into phi n. Note that since it is a scalar, it does not matter, scalar, the transpose of itself is this. So, therefore, V b n of t is equal to omega n squared L n into y n of t, where L n is this quantity. Okay. So, for this particular problem that we were solving, what did we get? Look at it, let us look at it. We are going to get it equal to V b 1 t is equal to, let us look at L 1. So, it is going to be equal to omega 1 squared L 1 into y 1 of t. V b 2 is equal to omega t squared L 1 y 2 of t, and V b 3 is equal to omega 3 squared L 3 y 3 of t. Now, L 1 is phi 1 transpose m into 1, and doing that we see that this is equal to 28,687.5 kgs. L 2 is equal to 9835 kgs. L 3 is equal to 6762 kgs. Note something very interesting, and that is that L is also a quantity which decreases with, but this is a force response. Note that even if these goes down, they are multiplied with omega n squared. Okay? And that is why for force responses, You will see that if you put this in and you plug it in and put it in, you will see that VB3 also contributes significantly in this particular case with your this thing, and therefore, yeah. So, the force response requires more modes because they are actually multiplied with omega n squared. So, this one is lower, this one is higher, but this one is lower, but this one is higher. So, as your omega n is being multiplied, the contribution of the higher modes to force responses is more than to displacement responses. Okay? This is another very, very important aspect that you need to consider. So, therefore, if you are looking at force responses, you need to consider many more modes than you need to consider. For example, typically, I will just give you some idea of some problems that I have solved. That I had a problem where I had 1500 degrees of freedom in a structure, okay, fairly complex structure. So, I had 1500 degrees of freedom, okay. To get accurate estimates of the displacement responses, okay, I required only 3 modes. To get accurate estimates of force responses, for example, bending moment, base shear, story shear, all of those, I needed about 50 modes. Okay. So, very less number of modes if you are looking at displacement response, more, but still 50 is significantly lesser than 1500 modes. Okay. So, that is the beauty of the mode superposition method. Okay. I am going to stop here and see you next time. Bye.